All right. Yeah. So yeah, thanks everybody for coming. Actually, yeah, let's go. Sorry. Yes. So welcome to this event hosted by the IoT Plus network. And first of all, definitions. What's the IoT Plus network actually? So we're a decentralized network with contacts and solutions for all questions relating to the Internet of Things. And this sounds a bit abstract, but you're going to understand what it is. We're basically a professional network of companies and individuals like me, like you are. I'm, for example, a private member. My company is not actively taking part on this, but I am as a member. And yeah, who I am, just like, so I can just keep going. Basically, yeah, I'm a solution engineer at a company called relayr, and I'm a private member of the IoT Plus. And yeah, I've been dedicated to IoT since 2015. So that was like maybe the infancy of the industry, but it's not about me anyway. Like who are our guests today? We have here Olga Lysak, who is the business development representative at Lemberg Solutions, representative for Germany, if I'm not wrong. And she will probably explain later what's her forte, but like I just like summarized here as business needs and services of a Lemberg solution. Sorry. And we have Dr. Volodymyr Andrushchak, who is a data science engineer, also at Lemberg. And as you can see here below, but yeah, he's gonna have the big chunk of the technology presentation today. So you'll get to know him better. And yeah, I'm going to give you guys a very quick background of what's the IoT Plus, or basically so you can understand the founding members of this network, set of companies, as you can see, companies in different. For example, we have here from accelerators to actually a technical university to a motion lab, which is like a ideation or even fab lab, a hackerspace type of thing. Code University. Berlin Partner, which is actually a company. It's not the. It is not also. It belongs, I believe, to the city of Berlin, but it is a company. And Team Neusta, another company for innovation, building minds. But yeah, you will get this presentation later, so you can, if you want to dig into any of these of our founding members, it's going to be very, very easy for you to find information. And yeah, just quickly talking about this because I found it interesting that, to see that this is actually part of a bigger thing. So yeah, the Digital Hub initiative of the Ministry of Economic Affairs. Sorry, my chat is actually blocking my own view. Ministry of Economic Affairs and Climate Action that supports hubs in Germany, and this type of hubs are centers, or I would say like institutions for developments for the development of a certain technology, of a certain field or certain business. I'll show you later a quick map. And yeah, aside from that, we're part of this Germany Trade and Invest, which is actually again, it's also like a bigger group to basically foster innovation and trade, basically trading partners in Germany and out of Germany. And yeah, just wanted to show you that, as you can see, there are many of these hubs, and we are based in Berlin. And as you can see, the topic of Berlin is IoT and FinTech. So it suits us very, very well. So that's why we remained in this city. And basically the purpose of the network, we just want to promote cooperations, because at the end, as I said, we're a network of companies and individuals. And the idea of this is to link people with people. So link people that want certain services with people that can offer those services, or people that want to work in a specific field, and companies or projects that actually need that type of people. So that's our idea, to create a professional IoT service portfolio, like a one-stop shop for all your IoT services, a place in which you can find any professional for any field that you need within the IoT umbrella. And yeah, of course, this also includes like initiatives for education and training, because it's in an ever-changing environment like IoT. You need to keep up to education. You need to keep up training and learning, because the technology is just changing too fast. And eventually, aside from these services, we'd like to support companies with setup and growth, which means it is sometimes easy to develop an idea and to come up with a proof of concept. But another completely different thing is to be able to productize it and to put it on the market and grow and come up with a sustainable business. And yeah, our expertise, as you can see, any of you working with IoT knows that all these fields are actually involved, especially, of course, hardware IoT devices, the connectivity, the second most important, for sure, gateways, edge computing, and then, of course, anything software like middleware, IoT platforms, and then topics that are a little bit more new, like relatively new, like data, like device management, data management, services and integration, of course, like integrating different services with each other, and then artificial intelligence, blockchain, and digital ledger technologies, which are also topics that slowly are coming together and basically infiltrating, so to say, the IoT world, that they were once more disconnected. And industries that we address, of course, Industry 4.0, which is the next big shift on industry, which is actually, it is happening slowly, but it's happening. Energy and utilities, IoT is having and is going to have a huge impact on the energy market. Mobility, we can see it. You can just basically see it like connected cars. You can rent a car, rent scooters, rent bikes that are connected. And of course, logistics, transportation, like tracking devices for inventory tracking, etc. E-commerce and fintech, one of the also biggest changes. And then anything connected, also at home, like smart home, smart living, health, smart devices, wearables, etc. And then, of course, farming, agriculture, forestry, and heavy industry, like mining. Again, slowly getting there. John Deere has harvesters that are connected to the internet. So yes, it's happening. Activities that we run, I'm almost there. I'm almost finished. Meetups and matchmakings. So basically putting professionals together, people that need something specific, a service with the right person. Innovation sessions, startup pitches. For example, when you have a good idea for a startup and you are not really sure, or you can pitch it before, you can tell us your idea, and we'll validate it or tell you, hey, maybe this is good, maybe this market is saturated, maybe you could think about this or that. Or if you're looking for funding, basically people that are willing to invest in your idea. And obviously, we also address workshops, hackathons, on-site workshops. I had experience in workshops as well, like by myself, electronics mostly. Hackathons. So, for example, this webinar would be part of our activities. And skilled labor acquisition. That means companies that actually require people, professionals in a certain field. We plan to. We are capable of addressing this need. And that's it. For now, let's network. So I'm going to stop sharing my screen and I'm going to just shut up and pass the ball to, I believe, Olga. Correct?
Yes, that's correct. But I think Volodymyr will share the presentation. And
yeah.
Then,
sorry if it was too long. I tried to keep it like very fast. I thought it was a good thing to give a bit of overview, you know, what we are actually doing here.
Yeah, that's good, because if you do that at the end, like everybody is tired and has not very much time to listen to, so that's why it's always better to do such things at the beginning. But I'll also try to keep myself short in order that Volodymyr has the chance, in fact, to make the main part of this webinar. I'm very glad to be here. So as Jaime told already, I'm responsible for business development in Germany. But in fact, I'm also head of AI business development at Lemberg Solutions, and I'm taking up a lot with our AI projects. Connected also, part of them is connected to IoT, as the same as today's topic, battery management system. Like 3 words about Lemberg Solutions. We are a Ukrainian IT servicing company or tech consulting company, active in 3 fields. It's IoT, both embedded and hardware development. So we can in fact develop the complete prototype. from the scratch, in fact, still including also industry design. One part of our services is web and app development, and the third part is AI solutions. So we work a lot with German clients. In fact, I would say 50% of our clients come from Germany. That's why I'm based in Germany, in Hamburg. And the company is already for 15 years in the market. I think Volodymyr can pass to the next one. So today's topic is AUTOSAR development for a BMS, like for battery management system. And we've done this project for a big car producer from the States, one of the biggest companies in the world. And unfortunately, the project is under NDA, so we can't tell the names. But it was a development for a hybrid car, and in fact, on the 48 on a 12 volt car battery. So we've done a lot of things there. You can see it's like a dashboard where you can see the main points connected to this project. So in fact, we've done such things as calculating the state of charge, the state of health of the battery, CAN communication, FET manager, a lot of diagnostic features. And on the right, you can see also the technologies used there. In fact, this dashboard is more or less like it's the main overview of the project, and we can return at the end more in detail to these key features and technologies. But I think Volodymyr, he's our data scientist working with hardware. It's like not a very often combination, but he's the one who was really deeply involved in this battery management system project. And he would deep dive in technology and how the project has been done. And at the end, I think we would like to answer your questions and discuss. So if you have like any also questions to key features or technologies, you can ask them. So Volodymyr, the stage is yours. You can go.
Hi, my name is Volodymyr, and I'm data science engineer in Lemberg Solutions. I like to work with different algorithms for embedded system. And today I want to discuss and present one of the key features for BMS, like state of charge and state of health algorithms. So first of all, we discuss about the current BMS on market and its features. And based on this BMS, we discuss why we need still custom state of charge and state of health algorithms. The main technical part is about state of charge and state of health algorithms, about existing approaches, our approach, and estimated results. And in the end, if you want to develop own state of charge and state of health algorithm, what do you need to do it, and what is the right roadmap to do it with the best accuracy. And however, you will have all interesting references where you can find more information about this topic. Oh, okay. A few words about terms. So first, state of charge is a ratio of current capacity of battery to total capacity of battery. State of health is a ratio of total current capacity of battery to manufacturer value. Equivalent circuit model is an electrical circuit that represents behavior of battery. Open circuit voltage is a dependencies between state of charge and range of voltage our investigated battery. Kalman filter or extended Kalman filter, mathematical algorithm that allow iteratively reduce the error of estimated results, in our case, state of charge. So let's move on why we need BMS. Yeah, so we know that BMS can provide one, two, or several features, and main feature is battery monitoring, just to measure primary parameters like voltage, current, and temperature. More complicated feature is battery protection, like over voltage and under voltage protection. It means that we try to increase time of life of our battery just to decrease the probability of crystals and gases in environment of anode and cathode our battery. The third feature is our estimated parameters like state of charge, state of health, state of power, state of life. So we can't measure this parameter like temperature or voltage. It means that we can only estimate this value. More complicated algorithm like balancing algorithms just use the previous estimated value and primary parameters just to balance capacity in battery pack that consists of several cells, for example, 10 cells, 100 cells, during the process charging and discharging, also just to increase time of life of our battery. And last things, if something going wrong, we need to report it to external device that, for example, we have a high temperature on specific cell, or we have a problem with the state of health on specific cells, please change it. Okay. What we have on market according to these features. So first of all, we have simple BMS. We can even call it like measurement or monitoring system. For example, from analog devices, where this BMS can provide a primary measurement. I mean, we can measure just primary parameters like voltage, current, and temperature, and just the same from Panasonic. Yeah, more complicated BMS also from Panasonic, but it can provide more complicated feature over voltage and under voltage protection, as I said, just to increase time of life of our battery. But one interesting thing that this BMS can work only with lithium-ion battery. It means if you want to use ferrum photos battery or lithium polymer battery, you can't use this BMS. More complicated BMS, for example, from Texas Instruments, support different type of batteries. It means that you should to put a specific value for specific register, and BMS will know which model, for example, open circuit voltage or ECM model used for this type of battery. However, this BMS has a specific domain for electric vehicles. And last interesting, BMS is from Maxim Integrated, and just the same features like in previous BMS, but we have state of charge algorithms with accuracy nearly 1% according to the datasheet. And this algorithm is based on column counting and open circuit voltage model. You know that column counting is just a basic algorithm. We can just count discharge and discharge current and estimate capacity of battery. But we know that we have different electrochemical effects in batteries, and open circuit voltage allows to fix this error for column counting algorithm. But why we need different BMS? So I think you know that one is very popular technology, beacons. We know that battery in this device can live 3, 4, or even 5 years, and we don't need to charge this device, or we can just change this device. But we need just to get information, to send information to users that, okay, you should change your battery, for example, in 1 month. And we work with really small current, microamperes. And in this case, you don't need to have BMS. It's enough to have, for example, open circuit voltage dependencies or just cutoff voltages. More complicated application is our smartwatches. So first thing is that we use this device in different environments, especially temperature environment. And we can charge this device every day or in 1 week or in 1 month. And we want, for example, to use this device several years. And the important thing here is like over voltage and under voltage protection that should increase time of life of our batteries. But the state of charge is not so critical for this type of application in comparison for the insulin pump. You know, imagine that your insulin pump shows that the state of charge is nearly 5%. and you think, okay, it's enough for this day. But you notice that in 2 hours, the state of charge is 2%. What happened? So it means that there is a problem with the state of health of this battery, and you need to change this battery. And in this case, the state of charge and state of health is really critical parameters, because it can create a problem for human life or health. And last example, electrical vehicles. So in this case, state of charge is important, like additional value for your product. Imagine that accuracy of state of charge is nearly 10%. And it means that you can add extra 5 kilometers for your electric scooter. In other case, imagine that you have accuracy 2 or 3%, and it means that you can add 5 kilometers for your electric scooter, and it can add additional value for your product. So a few words about my own experience. A few years ago, I was co-founder of a small company where we manufactured specific hardware and software for different plants and factories. And we and worker should wear specific trackers, and we need to charge and discharge this device every day. That's why our battery can die very quickly. And we work with different environment. I mean, like in temperature environment. And as usual, our battery can live nearly 6 months. And we have problems that our battery can die unexpectedly, and we create a problem for our clients because we can't record, for example, data in 1 or 2 weeks, yeah. And in the end, we just integrate the algorithm in these trackers, and we can estimate the state of health of our batteries. So we didn't fix a problem, I mean, with battery, but at least we didn't create a problem for our clients. And we notify the support technical department that there is a problem for specific battery. Please change it in specific wearable devices. And just to emphasize why we need a custom state of charge and state of health algorithm. So the first thing is accuracy for specific type of application like insulin pump or electrical vehicles. But you know that BMS can provide necessary accuracy, but you don't know if you can get this accuracy in all environment, I mean temperature environment, for specific type of battery or for all range of currents. However, if you work, for example, with electric vehicles, and you know that your battery consists of several batteries, it's a battery pack, and you can have even 10 BMS, yeah, and you need, for example, 2 or 3 seconds on a real microcontroller to get information about state of charge from all cells. And it can be a problem because you don't have 2 or 3 seconds, you need 1 second. And in this case, you just need to simplify your algorithm. Maybe you lose in accuracy in 1-2%, but for more complicated algorithm, like a balancing algorithm, it's more than enough. And different type of batteries also influence on accuracy of the state of charge. For example, manufacturer to decrease capacity of your battery, for example, in 1%, and it can influence on open circuit voltage characteristics. And you need to or integrate a new model or just to do own algorithms. And important things, especially when you work with higher current, is electrochemical effects in battery. And you should pay attention on it because in the end, you will have a poor accuracy. Yeah, and we will talk about it in the next slide. Let's move on to the main technical part about state of health and state of charge algorithms. You know that according to the state of charge, there are a lot of approaches for estimations as well. For example, simple approach like lookup tables. It means that you can have a huge array or huge table or specific model where you can, by using temperature, current, and voltage, find necessary state or charge value. It's a good solution with high accuracy, but one problem is that happen with integration in real application, because you don't know the size of this table, and maybe for specific type of application you can allocate specific amount of memory for this case. Yeah. Other type is based on filter in our case Kalman filter. So why it's important? Because Kalman filter can iteratively reduce the error for your system. In real application, you can pay attention on all environment, all cases. You don't know about specific all state of your system, but this filter allow iteratively reduce the error and for any system according to source noise and other problems that can happen in your application. And for example, also you can use a deep neural network or machine learning algorithms, but in this case you will use the same lookup tables, but in the end you will have additional problem which you have with deep neural network and machine learning algorithms. So in our approaches we use extended Kalman filter. So first of all, as I said, we use this algorithm because we can iteratively reduce the error. So step by step, we can get necessary accuracy. And however, there are a lot of literatures and articles where you can find any modification of this algorithms for different type of application. So it's important because you can find necessary information or fix your own problem. And important things is a high speed of running. It's important for our case for automotive project where battery can consist of a lot of cells, and we need to know, that imagine you drive a car and the power consumption in the first second is not the same in 2 or 3 seconds, and we need to know about state of battery right now. Okay, a few words about our algorithm, and on the next slide we move step by step about all this part. So first of all, you need to measure our primary parameters like voltage, current, and temperature. Then we move on to our EKF algorithms. So according to the predict part. So predict part, it means that based on state of battery and current consumption, you can predict state of battery for the next step. In update part, you just fix this value based on real measurement. Okay, let's move on step by step. So first of all, you need to record open circuit voltage, the characteristics that show behavior of your battery. It's the dependencies between voltage and state of charge. So how to do it? You need to discharge or charge your battery slowly. Literature advises to do it with real small current. For example, if your capacity of battery is 3000 milliamperes, and is divided by 30, it's nearly 100 milliamperes. And you need to switch off your load. Why you need it? Because imagine that you have a battery, but open circuit voltage should show like voltage inside of battery. So that's why you need, when you record this characteristic, switch off your load, your resistor, for example, on 20 seconds, and then switch on. And finally, you can build like average characteristic. And in application where you work with small current, I think until 200 milliampere, you can use only open circuit voltage characteristic for determination. For estimation state of charge, you don't need more complicated algorithms. Here you can see open circuit voltage with which, so this characteristic was recorded with current C divided by 5. So yes, you can record it with higher current, And in real application, you can use two characteristics. For example, when you discharge, one characteristic, when you charge your device, other characteristic, or just find average characteristics between this between a charger and discharging this process. So it really depends on your type of application. One interesting thing, you know how to integrate open circuit voltage in your final application. Just the same case, you can save it like a huge lookup table, or in this case, you can just represent it via polynomial, real polynomial. You don't need to have a deep knowledge in data science. You can just open a website where, just open a website and you can upload your data, and this website returns a trained polynomial, and you really save your memory. Next step, next part of our algorithm is equivalent circuit model. So as I said, this model represents behavior of our battery, electrochemical and electrical effects. So as you see that, first of all, we have open circuit voltage, like a voltage inside of battery. Yeah, that's why it's important to have OCV dependencies with high accuracy, because like it's a first step of your equivalent circuit model. So the next thing is an internal resistance. So you know that battery has internal resistance, and you can find this value in datasheet if you, of course, buy original battery. And it's a small value, it's nearly 18 or 20 milliohms. But you, of course, when you use it with higher current range, you will have a higher voltage drop in this segment. It means that final voltage is OCV minus voltage drop on this segment. It means, why it's important? So imagine that lower cutoff voltage is at 2.8 volts, okay? But you see that your ADC returns 2.7, and you think, oh, it seems something going wrong. It seems that I just over discharge my battery. No, because real voltage inside of battery is 2.8, for example, and it means that you can still use your battery even when you work with in the under cutoff voltage, and just the same when you charge your battery. Yeah, it's the first thing, internal resistance. The second thing is, you know, when you switch off your application or just load, you can see that voltage slowly changes. Yeah, in 1 minute, 2 minute, hour. It means that there is a transitional process inside of battery, and you can represent it. We are using parallel connected RNC element. It means that you can find this value to represent this internal transitional process. And last thing, when you work with higher range of current, you should pay attention on hysteresis. It's electrochemical effects. So it's electrochemical polarization. Yeah. And when you work with higher current, for example, even it's 1 ampere is a critical, I think that you should pay attention on hysteresis. If you don't pay attention, you will have a poor accuracy. And that's why when you select, for example, a BMS, and you don't want to develop own state of charge or state of health algorithms, you should check if there is any model that pay attention on hysteresis for your current range. Okay. How to determine, how to calculate this value? This value is for equivalent circuit model. So we know that we can find the internal resistance in datasheet, or we can find this value by HPPC test. HPPC test is a number of rules how to discharge and charge your battery to get this value. So first of all, you can discharge or charge your battery with current that is equal to battery capacity. It means my battery capacity is 3000 milliampere. It means that I should charge or discharge with this current for HPPC test. So I just try to discharge my battery on short period of time. In this case, it's minute, it can be second. And then I switch off my load, my resistors, and from this voltage, from this delta V, I can find internal resistance. Yeah, of course, you can find it in datasheet. However, you can find R1 when you observe this transition process according to this time. Of course, it can be 4, it can be 5. It's not one rule how to calculate these values. So, but at least according to the observation time, you can find the R1 value. It can be also milliohms, and capacity can be in kilofarads. Yeah, it's real value. And last thing is a hysteresis. Sorry, a few words about this test. So in real application, when you want to get a high accuracy, you need to develop one more algorithm that trying to find the optimal these parameters. Because honestly, if you work with small current, I think until 1 ampere, you can do it manually, for example, with using oscilloscope. But when you work, for example, with 2, 3, 5 amperes, you need to develop one more algorithm to try to optimize these parameters. And last thing about hysteresis. So why it's so critical, especially for this type of battery, ferrum phosphatus, yeah. So you know that for this type of battery, we have a flat curves according to the state of charge in a range from 10% to 90%. Yeah, of course, it's really cool for our application, but when we have a hysteresis effect, it means that we can, for example, the same voltage, 3.2, understand like 10% state of charge or 20% of state of charge or even 60% of state of charge. So in this case, you really should pay attention on hysteresis when you work with this type of battery, because the difference is really small and you can create a real problem for your end application if you don't pay attention on the hysteresis. And I will try to explain how Kalman filter works with a simple boxes. So I didn't put mathematics in the slide because we need one more topic if we want to understand how Kalman filter works. So first of all, imagine that we tried to estimate the weight of gold. Yeah, and we know that it's constant value, yeah, like a green line. We try to measure this value, it's a blue line, and red line is the estimated value. So what does it mean in our case with state of charge? Yeah. So first of all, we need to find a default value. What does it mean, default value? It's the first value, because we need to put a first value for our algorithm. So in this case, it's just measurement value, just the first value. It's the first iteration of our algorithm. It doesn't mean it's a first step, it's a first iteration. The second iteration is we try to decrease this error. What I mean? Imagine that our capacity of our battery is, according to the state of charge, is 99%. Okay, but we know that we try to estimate the state of charge every 1 minute. It's enough for our application. We know that current consumption is 1 ampere. We know that we can lose capacity of our battery, for example, 50 milliamperes, and it means that final final capacity will be, according to the state of charge, will be 98%. Okay, it's our predicted value. So we know previous state of our battery, we know current, and we can estimate this value, for example, based on column counting algorithm. We just predict this value. Okay, and right now we just want to know about the real state of application. So that's why we try to measure voltage in real cell. Okay, then we look at our equivalent circuit model, try to find a real voltage inside of our battery, and based on the real voltage inside of battery, we can, for example, estimate that final state of charge is 97%, not 98. And in this case, we have measurement value 97%, predicted value 98, and we have difference -1%. And we have one additional block like Kalman gain. So it's a gain that try to minimize this error, the differences between real and estimated value. So also there are several rules. I didn't put it on the slide because it will be so complicated. And for example, Kalman gain is nearly 0.5, and the final difference is -0.5%. And we just add predicted value, and we have 98.5%. It's our estimated value. It's our corrected value. And it means that we step by step will try to decrease this error. So we try to decrease the difference between real value and wrong value. But in our application, we use extended Kalman filter. Why it's extended? So we know that our open circuit voltage is not linear characteristics. So we have nonlinear behavior in the end and on the beginning. It's not all characteristics because we work in range to 4.1 volts. And as you can see that we have derivative function that shows the speed of change of our function. Why it's important? It means that we will have a pure accuracy of estimation in this range and in this range. That's why we integrate this function in our algorithm, and algorithm knows that, okay, here we will have a problem and we can pay attention on its nonlinear effects. And just to summarize how our algorithm works. So just the same, measure primary parameters, and we try to predict our state of charge based on the current, yeah? And here we have additional parameter like temperature. Why it's important, I will explain on the next slide. And based on state of battery, previous state of battery, we try to estimate a state of charge. Yeah, just to predict. And in the next step, based on a real voltage and Kalman gain, we just try to update to fix the final value, and its value that our algorithm returns. Okay, why is temperature is important, especially when you work with critical devices, critical application like insulin pumps or electrical vehicles. So because temperature influence in this range of state of charge. So it means that the speed of change state of charge will be higher if you use, for example, one open circuit voltage characteristic. What I mean, for example, if you work in temperature range, room temperature, for example, 18 degree or 20, yeah, the OCV, you should record open circuit voltage, for example, even for 0 degree or -20 degree. And when you measure a temperature on your battery, you should take open circuit voltage for your temperature. And in this case, you will have a higher accuracy. Because imagine you have a wearable devices, you are working at home, and then you just go for a walk and you have -10 degrees, and okay, something going wrong. But one more thing, So the negative, the minus temperature, it doesn't mean that it's discharged faster. It means that you can get all capacity that you have in battery, because when you back in your home, it seems that I have additional 1, 2, 3% to my state of charge. Yeah, important things. And estimated results. So first of all, we have a wrong estimation of state of charge. It's our default value. It's nearly 70%. Okay, here we just try to run state of charge algorithms every 2 seconds. And you can see that with different current, we have different behavior. So it means that when we have a higher current, we can get faster necessary state of charge. Why? Because when we predict state of charge, we know that our state of charge will change faster. Of course, because because our current is higher, and the speed of change will be higher. When we work with, for example, with a current less than 1 ampere, of course, it will be slower. And you have a question why we have different behavior. It's just the same, but it just should be the same state of charge, because in this case we work with current that is higher than 1 ampere, and here in this model we didn't put hysteresis, and it means that polarization electrochemical effect influence on estimation state of charge. So it means that we still have energy in the battery. Yeah, maybe we can get a right measurements voltage, I mean, in our ADC, but we can get additional capacity. But if we don't pay attention about hysteresis, we have a poor accuracy of state of charge. Okay, let's move on to the state of health, more interesting and more complicated algorithm. So at least in my opinion, because it's not so easy to estimate this parameter, this value in real application. I also emphasize the things about integration in real application because I work with integration, and I know that some laboratory things, some laboratory algorithm can work in real application. So you know, the state of health is a ratio of total current capacity to manufacturer value. Of course, when we charge and discharge our battery, we lose our capacity. So first of all, it's happened we lose of active materials on electrode. It means that we lose a square where we can save our active materials, in this case lithium. And of course, when we lose a lithium, yeah, so it means we can restore this energy. But additional problem is that we can add a problem to our battery when we don't know the correct range of voltage for our battery. It means that we should to integrate over voltage and over voltage and under voltage protection. So, and in this case, we decrease the probability of creating crystals and gases in our environment because we create ions disbalance. Yeah, it means that we can, that it's in one case we don't enough necessary ions, and in the other case we have too much other ions. Okay, and in this case we don't have so many approaches in comparison to the state of charge algorithm because it's a little bit complicated, more complicated algorithms in comparison to the state of charge. First of all, of course, we can use experimental method, like just to measure internal resistance. Of course, when you charge and discharge your battery, internal resistance is changed, but it's not possible to measure this value for all type of application, you know, especially small application. And or you can just even use basic column counting algorithms. For example, we just can count our discharge and charge current and estimate final capacity, but we have a poor accuracy even for the state of charge algorithm. It will be worse even for the state of health. Just the same, like in previous case, we use features that can show that something going wrong with our batteries. So in our case, we just record a charging characteristic of our batteries. And in this case, you can see etalon values, etalon rows. When we lose 4, 5, 6% of total capacity of our battery, and you can see the characteristics that show how it's going on. However, you can see that we have interesting places like regeneration. It means that we can renew specific amount of capacity. It also can happen when you charge and discharge your battery every day. It's really cool for end application, but it can create problem for estimation state of health, and we will see it on the next slide. So in our case, we try to find features that will show that something going wrong with the battery. In this case, we have 3 features. You can see on the beginning, when we charge our device, that there is a difference between rows in the end, and time of charging our device is also will change. One interesting thing, I think, on my opinion, from my experience, that state of health algorithm, it's very individual algorithm. So it means when you can find algorithms like an open source project, and it seems that model is just the same as according to your battery type, but in real application, it can create a wrong estimation state of charge. Why? Because you can work with different temperature environment or different current range. However, manufacturers like to modify a battery, and your behavior can be completely different. And I suggest, even when you want to use a BMS in production just to test it, you can just charge and discharge your battery, for example, 100, 200 cycles you need, and you will see that you can just check if this BMS can provide in correct way estimation state of health. And on this slide, you can see the different type of battery, and you see the behavior is completely different. So it's not like OCV that, oh, it seems that something changed. We can estimate simply state of charge. However, when you work with state of charge, you should pay attention on the state of health just the same in this range of open circuit voltage, because like in case with insulin pump, you can show information for end user that, okay, you have 5%, but in 2 hours you have 2%, and it can create a problem. Yes, that's why the state of health is additional task for state of charge. Okay, and finally, let's discuss our algorithm. So one important thing, in literature or articles, you can find that 0 state of health is 80% of state of health. It means when you lose 20% of state of health, you should to change your battery. And sometimes you can find that just to know how to correlate 0 state of health in literature and this 50%. So first of all, we should select our etalon row according to the real state of health. And then when we charge our device, in our case, it is electrical scooter. And we know that we finished this process. And previously, we record our charge data, I mean voltage, and we try to find distance between current row and etalon values, with using statistical parameters like in this case is clip distance and mean epsilon percentage error. And in this case, we try to find a correlation to necessary state of health row. Just the same case, pay attention on memory allocation, because you can use, for example, state of health even with a small step, and you can have a huge lookup table, and you can just the same use a polynomial just to represent behavior of your battery. And on this slide, we have estimation of this algorithm, where the blue line shows our results. And you have a question why we have a poor accuracy in specific places. So first of all, we have a poor accuracy after regeneration, after this step, and in here. So it happens because the charge row is really similar to one of the previous, and we can skip, or yes, we can decrease the error only in one way: how to select in the right way our etalon charging rows. However, we can completely wrong estimation. So yes, sometimes it really happens in production. I mean that charge row is really similar to state of health when we have 96%, but you can just skip it if you have a history of your battery, or you know the battery, that user can change this battery. Yeah. And on this slide, you can see the error estimation. The average value is less than 2%. For our case, is not so bad. Because you know that, for example, in electric scooter, you have 10 battery cell in serial connection. And for example, if one cell has low voltage, yeah, and can create a fire, and you should to detect that something going wrong with specific cell. Yeah, and let's move on to the last part. If you want to develop own state of charge and state of health algorithms, what do you need for it? So, of course, you can do it at home with just to find necessary elements. But first of all, you need to know about battery behavior, and you should to start with open circuit voltage, just to see what happened with your battery. So it's important to know the behavior, and you just to record open circuit voltage characteristic with slow current, and also with this pauses when you switch off your load, just to see the transitional process inside of battery. You see our schema based on Nucleo board, so you can just use the schema for open circuit voltage, or even for testing state of charge, state of health algorithms. Important thing, according to the state of health, if you want to have a high accuracy state of health, a state of charge, or you are working with critical application, you need to work with you need to develop state of health algorithm, and you need to discharge your batteries, because you need to know own features of your battery that can show that you lose capacity. One more interesting application, you have a link, you can check it. And of course, professional equipment. Yeah. So in one of our projects, we have a company that can provide necessary data sets with accuracy even 6 point of the mark. It's important thing for laboratory testing when you can simulate it in MATLAB, in Python, but you should remember about noise in real application, especially for electrical vehicles which work inside of a box, and you should pay attention it even when you just simulate your algorithms. And a few words about roadmap. So if you have a BMS that can provide necessary feature, I think you don't need to develop own state of charge and state of health algorithms. You just need to know that this BMS will work for all necessary environments and can provide necessary accuracy for all your cases. But if you need to develop own algorithms or BMS can provide necessary features. Of course, you need to develop own state of charge and state of health algorithms. And remember about three things: is accuracy for your system, integration complexity, because you know that it's simple in Python or MATLAB, but it can be simple in final algorithms, and typical algorithm complexity or notation. So if you want to use EKF approach for estimation state of charge, first of all, of course, you need to record OCV characteristic, find parameters for equivalent circuit model. You know that you can delete just equivalent circuit model and use, for example, neural network. So it's also possible. It means you can change any block. If you can do it better with other algorithms, of course you should do it. So it means that you can estimate, for example, final voltage that is important for EKF algorithms. And if you work with higher current or work with ferrum phosphatus battery, don't forget about the hysteresis effect, because it will influence on final accuracy of state of charge. Test it in MATLAB and Python and convert it in your final code for your microcontroller. With the state of health, you need to find own features. You need to discharge your batteries. You don't do it with 1 or 2 batteries, because it can be out of statistics. At least you should work with 3, 4, or 5 batteries. And you just need to discharge and charge your battery according to limit of your battery. It can be 400, it can be 2000. Then you can find features and then try to correlate these features according to your final state of health algorithm. And important references. Here you have also data sets where you can estimate state of health in your own way. But honestly, this topic is really popular for BMS, but it's not so easy to find open source data sets. And in most cases, you need to record own data, and it takes some time. It's everything from my side. Thank you for your attention. If you have any question, you can even write to me in my mail, or Olga, maybe you have a business questions. Yeah.
Yes, if you have like any business questions, you can for sure tend to me. So, but it's like you can find on this slide, in fact, my phone number and my email address, and you can find me all the time on the LinkedIn or like at IoT Plus network, where I try to be like active enough. So if you can also come to the network and discuss with me all the questions. But I think like, thank you, Volodymyr. I think it was like, I got quite a lot, but however, I'm not a technical person. That's why, like, at some points I was a bit overwhelmed with the amount of technical information. But I think for all like for all techies present here, I think it was, on my opinion, could have been a quite valuable input. And if there are like any questions, please feel free to ask.
Yeah.
He's like very much eager to answer all of them, and I think he knows quite a lot about BMS. So please use a chance to ask him.
Yeah, I was going to tell you guys that we have actually a few questions, so I'm going to read them for you.
I think Michael wanted to ask something. I've seen he tries to show this on Zoom. So Heiko, do you have like the questions still? Or?
Yeah, I have the questions here. Yes. So one says, like, for testing the algorithms, I noticed that you were using a Nucleo board, logging data via teraterm and a simple buzzer.
Yeah.
But what do you use to collect the data, the data sets needed to develop the algorithms?
Okay, so it's the board is scheme is developed by my colleague. So of course, we need to have ADC and shunt to measure voltage and current, because you just need to count a current for estimation capacity. You know, because state of charge is a ratio current capacity to total capacity, and you need, in this case, to have a current. Voltage, because you need to build dependencies between voltage and state of charge. And of course, if you will work with different environment, temperature environment, you need to have a thermistor.
Yeah, makes sense to log the temperature as well, correct?
Yeah.
Mm-hmm. All right. I hope that was answered. Yeah, I'm gonna sorry, another one. Yes, is yeah, I guess it gets easier with every new development, but how long would it take to replace the model of the battery and recalculate everything for that battery?
Okay, so for example, if you need to integrate an open circuit voltage or change or record these characteristics, so you need at least 3, 4, 5 days just to record this characteristic, and you need just to apply this action maybe 2 or 3 times just to know, just to find average characteristics. And maybe you want to use not only discharge characteristic or even charge, and you work with really small current, and then you need to switch off your load just to see this transition characteristic. So it can take nearly, I think, 2 weeks, but it's only recording. Yeah, so you can do something else this time. Yeah, if you want, and it's not, if you have a characteristics according to application, you can integrate it. I think that it's not possible to do for a specific BMS because they have own characteristic. But if you need to calculate, for example, ECM parameters, yeah, so you need to do a HPPC test, or you can find this data in open source literature, like in datasheet you can find internal resistance, and even you can find R and C value, and you can even find a hysteresis model, because hysteresis will change according to the different range of current. I think the most time-consuming thing is the testing. Yeah, so I think that you will test at least 2 weeks, at least, because with different temperature, with different current range, or you just need to switch off your device and check the state of charge in the next day. So I think so you need maybe 1 month is enough to build a basic state of charge algorithm with high accuracy if you don't work with higher current, but if you work with 1, 2, 5, 6 amperes, it can be even years, even year. Yeah, it's because the hysteresis, yeah, the most complicated, yeah, because hysteresis and sorry, yeah, it's a hysteresis is really complicated things, and you need to represent this behavior, the polarization behavior, and when you lose capacity, the behavior will be different, and it's a complicated thing.
Correct, and the more you use the battery, you are actually on that process of losing capacity.
Yeah.
So it's like a vicious cycle, so to say. All right. Sorry, and I have another one actually. A question here from one of the attendees. And it says, sorry, I have to. It's a little bit rush, reading a little bit rushy. I checked one of those chips with BMS functionalities, and it said power supply support circuit. So you have to add extra components for to your design.
Yeah.
Are there already microcontrollers with integrated BMS functions? And if not, do you think this will ever happen? And then he says here, I remember when you had to put extra chips for things that are very common, like the USB to serial interface. That's correct, this FT232, whatever. And now they're all integrated in the microcontrollers. Okay, so I guess if someone that wants to know if you think that there are going to be microcontrollers with BMS features or microprocessors that already have the BMS, small BMS module.
Okay, got it. So honestly, I didn't. So I can't find BMS that is integrated in microcontroller, because you can have 10 BMS, for example, in our application we have 9, and we have one powerful microcontroller that works with this BMS. And I just think from the electric vehicle domain, okay? And for example, that future batteries for automotive, it's not one battery pack. So imagine that you have electric car, and right now you have one battery pack, but in future, they will try to put, for example, 10 battery pack in different places, okay? So, and you can change one battery pack, don't change all this huge battery pack. And this block should work with using Bluetooth or other protocol. So honestly, it really depends. It really depends on features, because if you need a basic feature from BMS, you don't need microcontroller. Yeah, so that BMS will report about the problem, because we don't care about technical things if that it works in the right way. And if we have a problem, we should to say it to our external device. It can be a microcontroller, or it can be computer. Yeah, it can be a computer board machine in our car. So I think that the BMS is like market, and we add these features. Yeah, it can be enough for you. If you want to add something, please select your microcontroller, do what you want, and I think that maybe it's possible for specific type of application. It can be, for example, as the space, that we need, or with for military type of application. It can be. But if we talk about like our typical market, about electric cars, wearable devices, I think that it's not so maybe important, even because that BMS at one value, for your system microcontroller is other. So we just need to run features, because BMS we can't add additional value only with using primary measurement or just to know the state or charge. Because imagine even when you use insulin pump, okay, user knows that he or she should change battery. But when you use insulin pump, it can be dangerous if you do it myself. Yeah, it's do or something else. You need to you need to know the company. You need to know where there is a service center, and you need to notify it about technical departments that this user will have a problem with battery in 1 week. It's more important, I think, that have all these features in one chip. At least in my opinion.
Makes sense. Yeah, also to offload, I guess the offload the task from the microcontroller. So you are basically another chip is taking care of that, and then you're
Even in our case, we use a real simple BMS. So in one of two our project, we use simple BMS that provide primary parameters, and we run all algorithms according state of charge, state of health, and balancing algorithms on microcontroller. We have powerful microcontroller because it's important to deliver a business logic. And in other our project, we have more complicated this maximum integrated BMS, and we try, why we use this BMS, we try to compare state of charge of this BMS and our algorithms.
All right, cool. Let me see. All right, I think that was all from the attendees. I had another question, but that's personal. I mean, not personal, it's technical, but it's came out with, but I'm gonna leave if anybody can ask or want to ask anything else. Otherwise, okay.
Maybe you are like you're already ready with the question, so it will be better somebody else has some technical issues.
Yeah, if you have any questions, I mean, you can write a letter, mail.
Wait, so I get to ask my question or not? Like because no, I saw that you mentioned that when a battery loses 80% of the
Yes.
capacity, you should or you must replace it. And I was actually interested because I have really old laptops that I can tell you the battery, I'm 100% sure is not 80%. Of course, they still work. They work like 10% of the time, you know, that I used to work. But my question is why you mentioned that you must change it?
Okay. So a short story. 1 year ago, when I worked on my dissertation, I just killed my battery. And right now, when my marks show 50%, it means that I have 1 or 2 minutes to get my charge device. Especially when I work with more than two, when I have at least two applications, not even 3, 5, so it can die in 1 or 2 minutes. So it's not. So it means that it seems just everything okay, yeah, but you are in fire, and I really am scared to open box to open the battery. I mean, I should put it in this. In the service center because it can be really dangerous. Not for me, for my computer, because it can be too many gases in this battery. Or crystals. It's I don't know what is the problem, or just over discharge or overcharge this battery. I don't. It's really interesting what's going on with this battery. So the 80% is just a good advice. So you know, because you can faster. So you have, for example, typical 18650 batteries, lithium-ion. You know that you have 400 cycles, you know, and in these 400 cycles, you can lose 20%. Okay, it means that when you use, for example, your battery in next 100 cycles, it will be 500. It can, let's say, company, the manufacturer doesn't provide a guarantee that it will work in proper way, or it can create even in fire for your electrical vehicles. Yeah, but okay, in electrical vehicles we use ferrous phosphatus, and you know that charge and charge discharge cycles is 2000. Yeah, it's a long. We have a long time of life of our batteries, and I think that it's just manufacturer guarantee that you lose this 20% when you work in limit the charge discharge cycles.
Yeah, okay, so it's more like exactly recommended, no, recommended action.
Yeah. Maybe
You
not
can't trust
must.
your
Yes.
battery anymore, no? After that, yeah, you shouldn't trust it.
It's like would be better you do this.
Yeah, okay.
Yeah.
No, I just was just curious because of the number. Like I thought, yeah, but I also have like power banks and things like this that are like completely inflated. And as you say, it's gas for sure, and could have like crystals. And I don't plan to
So
dig into them. But
on
regarding
one of
laptops, even if they don't have any physical, like apparently they're still like the physical integrity is still there, but the capacity I can notice that they don't last. They last a few minutes. But I was
okay, on one project we have limit 73. I don't know why, 73%, not 80, 73, but it's in case we use ferrophosphatous batteries. Yeah, it's for electrical car. But it's not so 60 because, imagine that you have an electric car and you lose 50% of capacity. It means that you lose 50% of your distance, like for your electrical car.
Yeah, exactly. It's not that they have a crazy long range. So
yeah.
they are 100%. The range is already sometimes in comparison with like a internal combustion engine. Yeah, they still yeah, but of course they'll get there. All right. I think that was okay. That was it from my side. I shut up. I guess if we don't have any other questions, then we'll call it a day. Right? So yeah, thanks everybody actually for joining. Nice. And you guys will get this presentation. Well, we'll release the video for sure, but I believe immediately we can just release the slides. So you have the links, because I noticed that the references and the literature basically used in many of these explanations, and also the data sets, for example, they were like quite long links that I don't think no one is going to write down. So yeah, you can get the presentations. You will get the contacts of Volodymyr and Olga in case you want to address to them directly. And I think that was it from our side.